Wow. I love that commercial. You guys probably don't remember it at all because it came out, I think, when I was in high school. But that's a Nike basketball commercial, and those guys just straight up kill it. I love it so much. There's some old NBA players in there. I think KG's in there. Maybe Darius Miles. Jason Williams dribbles two balls in there at one point. Go look up White Chocolate if you don't know who he is. You should learn today. All right. Um, but yeah, so I love that commercial. I used to watch it all the time back when it first came out. I would just scour the internet to try to find that commercial. All right. So anyways, share that with you guys. My high school days. Today we're going to talk about differentials. Okay, and now this is a very similar topic to what we did yesterday with linearization. Okay, and so before I talk about all this stuff on the left here, I want to talk about this graph on the right. Okay, and I'm going to see if I can highlight this in decently at all. Right, but here I have this function which I'm going to highlight in red. And I've already messed it up, but it's okay. Okay, and I'm just 2 points on this function I'm looking at. Okay, points P and Q. Okay, now the other thing I have on this graph is the tangent line to the function at the point P. Okay, and so what we're doing here is basically what we did yesterday. We're approximating what the y value is, except we're not looking for the exact y value here, right? So here's what we have, okay, 2 points P and Q. Now, the difference between their x values, dx, is just delta x, right? You take the two x values, you subtract them, and that's how you get the change in x right here, okay? Now, just like with yesterday, you know, kicking it old school, right? Say this is a really complicated function. We can't figure out exactly what the y value is at the point Q right here, okay? So therefore, we don't know what delta y is, right? We don't know exactly how far up we go in this function, right, when I go over delta x, right? Delta x is my change in x. As I go over to the right delta x, I go up a certain amount delta y. Okay, and if you have complicated functions or if you have crazy inputs for x, there's just some functions that are harder to evaluate. And so, using calculus, what? We're going to say that dy is going to approximate the change in y. And now dy here is the height difference between s and r. Okay, and if you look at these on the graph, right, delta y and dy are very similar. Okay, and so we're going to find dy, and that's what right here we call the differential, right? The differential dy is equal to f prime of x times dx, which equals the change in x. Okay, so we're going to find the change in y here, right? And now, you know, I can take that change in y, I can add it on to the y value at P, and I could figure out what the coordinate of r would be. Now, we're not going to do all of that, right? We're just going to solve for dy today. Okay? But the point here is that what we're solving for, this change in y, is useful for approximations, just like we did yesterday with linearization. Okay? But for you guys, this is what we need to focus on. Okay? dy equals f prime of x times d of x. All right, so that's exactly what we're going to solve for here. All right, so let's take a look at example 1. Whoops. Find the differential dy and evaluate dy for the given values of x and d of x. Okay, so here's my function, x to the 5th plus 37x. I'm looking at the point x equals 1, and now dx, which is the change in x, is 0.01. Okay, now this is positive 0.01, so I'm talking about moving to the right. Okay, as I move this function to the right, 0.01 units from 1, what is the change in y? Okay, that's what I'm looking for here. And so here's what I'm going to do. I'm going to take the derivative of both sides, okay, and now this is with respect to x. So the derivative of y is 1, and I don't want to write 1, right? But I will write dy dx. And that's going to equal 5x to the fourth plus 37. And now basically all I have to do is cross multiply here. I'm going to multiply both sides of this equation by dx. And so on the left hand side, I'm going to get dy by itself, the dx's cancel, and on the right hand side, I'm going to get 5x to the fourth plus 37x all multiplied by dx. And that is my differential dy. Now, I am specifically looking for the differential at one particular area. I'm looking at it where x equals 1 and the change in x is 0.01. So I'm going to plug in both of those values. dy equals 5 times 1 to the fourth plus 37 times 1 times dx, the change in x, 0.01. So dy is going to equal 5 times 1 to the fourth is just 5, 37 times 1 is 37, times 0.01 is the same thing as 42 times 0.01, and anything times 0.01 means I can just move the decimal place over left 2 units, so this is going to be 0.42. And that is dy. So from 1, as I move to the right 0.01 units, right, my graph moves up approximately 0.42 units. That's what we're solving for here. That's dy. Okay? All right, let's do one more similar example. Okay, y equals the sine of 3x. Now I want to evaluate dy at x equals pi, and the change in x is negative 0.02. So the first thing I'm going to do is take the derivative of both sides. So I'm going to get dy dx equals, now the derivative of sine is cosine, so this is cosine of 3x. And now I have to multiply by the derivative of 3x, which we know is just 3. So this becomes 3 cosine of 3x. Multiply both sides by dx, or you can think of this as cross multiplying, right? Doesn't matter either way. But you're going to get dy equals 3 cosine of 3x dx.
Mr. Cotero, please call the operator. Josh Cotero, please call the operator.
Okay, moving along. Now, we want to specifically evaluate when x equals pi and dx equals negative 0.02. So I'm moving to the left here. I want to see what happens to y. Okay, so dy is going to equal 3 cosine of 3 times pi, or just 3 pi, times negative 0.02. So this is going to equal 3. Now, cosine of 3 pi is the same as the cosine of pi, which is negative 1, times negative 0.02. So this is going to equal, let's see, negative 3 times negative 0.02, which is going to be 3 times 0.02, which is 0.06. So this time, as my function goes to the left, right, it also goes up approximately 0.06 units. Okay, all right, one last one here with differentials. X plus y equals xy. same directions here, right? Find dy when x equals 2 and dx equals 0.05. So, first thing I'm going to do, take the derivative of both sides. So the derivative of x is 1. The derivative of y is also 1. I'm just going to write dy dx equals, and now x times y, use the product rule. So this is going to be x times the derivative of y, which is 1 dy dx, plus y times the derivative of x, which is just 1. Oh, yeah. So now I've taken the implicit, I've differentiated implicitly, okay? Now I need to solve for dy dx so that I can solve for dy, okay? So this is 1 plus dy dx equals x dy dx plus y. So bring my dy dx terms to one side, bring everything else over to the other. So this is going to be 1 minus y equals x dy dx minus dy dx. That's supposed to be a y up here. That's supposed to be a d. Whoops. Okay, so now let's go ahead and factor out a dy dx. So I get 1 minus y equals dy dx times x minus 1. Therefore, dy dx equals 1 minus y over x minus 1. So there's my derivative. Okay, however, like we've been doing, right, I want to solve for just dy. So I'm going to take both sides, multiply by dx again, and so I'm going to get dy equals 1 minus y dx over x minus 1. Okay. Now, I want to evaluate dy. Okay, if I look back up at the problem here, right, I'm given a specific x coordinate. X is 2, dx equals 0.05. Okay, however, my dy here has a y in it. Okay, so the first thing I need to do is I need to figure out what the y value is when x is 2. So let me take 2 and plug that into my function over here. And maybe I should switch up the color. Okay, let me take 2 and plug it into that function over there, right? So that's going to be 2 plus y equals 2 times y. So subtract a y over, right? I get 2 equals y. So the point on the graph here is 2 comma 2. Okay, so those are the x and y values I'm going to plug into my differential along with the dx. So this is going to be dy equals, okay, my work just disappeared, so maybe it's not going to be, there we go. This is going to be dy equals 1 minus 2 times dx, which is 0.05, over x minus 1, which is 2 minus 1. Now, dividing by 2 minus 1 is just dividing by 1, so I'm going to ignore that. 1 minus 2 is negative 1 times 0.05 is just negative 0.05. And that is my dy. Okay. So as this function moves to the right 0.05 units, it moves down approximately negative 0.05 units. Okay, so that was the second half of the first day of 4.5 just on differentials.